Thank you very much for a kind introduction. Welcome to Cottbus and BTU. I hope you enjoyed your workshop or seminar or winter school, however it's called. So far, I heard that unfortunately the excursion yesterday was cancelled due to a demonstration. But I hope that some of the pictures can show you what you have missed. So my topic is about the cultural landscape that we find in the area of these open cast mines. And what you see here is a picture of the open cast mine Jenschwalde. And if you have a break and you go down this floor and you have a view, you will see exactly these, this is the power plant Jenschwalde, and you can see it from here. Yeah, and this is the open cast mine. So we cannot make it a little bit darker. Would be better for the slides. Okay, I will show you more details of this technique, and but this is a quite nice picture showing you the situation here north of Cottbus. Yeah, thanks. Just completely down. Completely down. If better, yeah. Okay, this is the conveyor bridge, which is a quite unique technique developed here in Lusatia, and I will talk about that later on too. So the outline of my presentation is listed here. As mentioned, my chair is called Geopedology and Landscape Development. I will talk a little bit about what we are doing, and then I will give you an introduction on the natural setting, and then I will focus on some aspects of archaeological findings here, and then show you what this is all about for our future research. I can send you a lot of papers, research papers, journal papers, PDFs that will give you more information about my talk and where you can have the primary source for this. Just send me an email, or I will give it to the chair here, and then he can distribute it. So the research we are doing is an integrative research, which means that we are studying the geomorphology, which is the landform of our Earth surface. We are also studying the pedology, so the soils of our Earth. And within the topography and the soils, there are two other aspects. One is the archaeological context, meaning so what imprint does we find from the human land use, for example, or from humans in general. And the other aspect is what does this mean for ecosystem, metafluxes, energy fluxes, something like that. So how does geomorphology and pedology contribute to aspects of geoecology, so to say? We work quite a lot in the field, which means when I talk we work in the field is that our students take a car, take a shovel, take these equipments as you see it here, make drillings, or just manually dig out the soil profiles. So once they did it, they can have a rest. Or we use heavy machines for doing larger excavations. And this is very special here in the area because we have a really large excavation, which is the open cast mine, and that makes it very, very unique here for doing our research. So by this field approach, we get insight into the quaternary stratigraphy, so the stratigraphy of the last 2 million years, and how the sediments develop and how the soils develop. And we reconstruct landscape development by that. So that's what we call landscape development. So you may have a different approach on the definition of landscape. So my understanding of landscape is that this is some kind of an ecosystem in an area that is controlled by several factors like climate, soil, topography, but also by humans. So and then we call it a cultural landscape when it's affected by human. And this impact or this human effect is not only a recent one, but we can have influence or changes of our ecosystem and our landscape 7,000 years old. With the start of early farming by the Neolithic people, we have the formation of the first cultural landscape. So this is my understanding of a landscape and the difference between a natural landscape and a cultural landscape. We use several techniques. I don't go into detail into this. ERT is electrical resistivity tomography, or SSR is shallow seismic refraction, GPR is ground penetrating radar, and all these techniques are used to get, we call it an indirect technique to identify structures or the architecture of the shallow subsurface. Shallow subsurface is a term we use in geomorphology to describe 5-10 meters below the surface. So we are not like geologists or geophysics interested in the earth crust and the inner core, something like that. We want to study the first meters or sometimes tens of meters where the soils are and where young sediments are deposited. So the one aspect is to study the subsurface by our outcrops, because what we see we can sample. The larger the outcrop, the better it is. If we don't have these outcrops, we use these geophysical techniques, as you've seen before. And the other point is that we want to get very detailed information on the topography, meaning that we want to get digital elevation models, DEMs, and this is done by surveying techniques. One surveying technique is a terrestrial LiDAR, so that's light detection and range. It's like a laser scanner, yeah? It scans the topography. Some of you may know it from architecture, something like that. You can also scan buildings. We scan our geomorphology. Yeah? And what we also use is these micro drones or UAVs, as they are called, and we use a quite sophisticated one that can produce digital elevator models by photogrammetry. So by the drone has a camera, and then by photogrammetry you can produce very good digital elevation models. So we have information on the subsurface, we have information on the topography, and then we are studying what is in these structures, in the soil and the sediment, and there's a whole variety of lab techniques I will show you later on. What is especially done by us is the field portable approach, meaning that we can take devices, as you see here, and take these devices into the field and do analysis on site. Yeah? So field portable near infrared, field portable X-ray fluorescence, and field portable X-ray diffraction. Especially that one is quite common, also used in archaeology to determine metal content or metal concentration in artifacts, for example. Sometimes you can produce fingerprints of the artifacts. And X-ray diffraction, you can identify minerals. This is quite unique because this technique is really used in the field. It's very rough, so it's not so, the detection limits are not so good as in for lab analysis. But for example, we use these field portable XRF to determine metal contaminations deriving from historic mining pollution. So for example, in the 15th century, we had a lot of mining in Central Europe. You may know the heritage site in the Harz Mountains, yeah? And in the surrounding of this metal mining, there was crushing of the ores, and by that distribution of the ores, and the ores are rich in heavy metals, and the heavy metals then accumulate, for example, in river sediments. Yeah, for example, we had a study where we identified a metal contamination, a lead contamination in an alluvial floodplain with amounts of 20,000 parts per million. So you can guess what is the upper limit which is allowed in Germany. So that's 1,200 parts per million lead. If you have 1,200 parts per million lead or more, you have to just clean this site up. And we have sites in Germany that have contaminations that 400 years old, and they have still these high amounts. So these are techniques we use for studying the past environment, so to say. A lot of lab analysis, I think I will skip this. A lot of soil physics to determine the texture, the grain size, the physical properties, etc., which is important to understand. How does our soil function? So in sense, does the soil, or is the soil able to hold lots of water for the plants? We call this water retention. Or in a sandy soil, you have a drainage of the water, and the soil is not able to hold a lot of water against gravity, and therefore this site simply is not very well suited for farming, whereas the other side is better suited for farming. So there's a lot of analysis, chemical and physical analysis, which is necessary for us to understand soil in sense of a function for land use or crop production. So there are different functions of soil. One is land use. And other chemical analysis like pH, you might know it's an easy one, or carbon content. Several chemical parameters are important to understand the soil as it is for our interpretation on the land use. So some pictures and names you see here. So of course we do this in a group. We have several PhD students working, technician, postdoc researchers. So this is just a part of my group working on geoarchaeology. So my group is about 12 people. So most of them work more or less in the geoarchaeology part. The funding we have for this research is mainly from the German Research Foundation, and we have a big project which is called Virtual Institute for Integrated Climate and Landscape Evolution Analysis. This is funded by the Helmholtz Association, and we cooperate with the GFZ in Potsdam and the Polish Academy of Science. And I will tell you some approaches and results of these projects now. So coming to the second part, giving you an introduction to what you missed yesterday and where you are. So we are here in Germany, of course, but nearby the Polish border. So from the geography, we have this unit in the south, which we call the low mountain ranges, and then we have this area which has very low elevations, and therefore it's called the Northern European lowland, elevations of 150, maximum 200 meters above sea level. And Cottbus is located here in this part of the Northern European lowland. We mainly find quaternary glacial deposits, and I will tell you in a minute what this means. So looking at the source and the topography, you see a block diagram here. So this is Cottbus, Berlin would be up here. So this is the Spreewald. Did you make the incursion to the Spreewald? Or? Yeah, okay. So you know this. You see 3 or 4 distinct geomorphic units. So in the northern part we have an upland, so to say, which is of glacial origins. This is the Weichselian part. So talking about the quaternary, we had this, as I said, is the last 2 million years. We have a fluctuation of warm periods and cold periods, and the last cold period is called the Weichselian glaciation, or the Weichselian cold stage, or Weichselian cold period. And this period of cold temperatures led to an increase of glaciers, and the southern limit of the Weichselian glacier, about 8,000, 20,000 years before, was situated here. So this was the southern rim of this huge phenoscandic ice sheet, and at the rim there was outwash from the glacier, which is called the Sunder, and then we have these huge valleys, which we call Urstromtal. That's also a term we use in English, or ice marginal valley. So the huge masses of water are then transported towards the North Sea, yeah, along these huge valleys. And in the southern part there are other glacial deposits, but these are older ones. So these are Elsterine or Salian glaciation. So Weichselian is the last glaciation, and Elster and Salian are older glaciations. So this is 120,000, 130,000 years BP. And what's the diagram also shows is that according to these geomorphic units, we have a distribution of typical soils, like the pot soil in sandy areas, or the Campi soil, which is the brown earth on the uplands. The other part is that you see these lignite mines, because under these quaternary deposits in the tertiary layers you find a lot of these brown coal, what we call lignite. This is a detail of the area here. You see Cottbus. Northeast is Jenschwalde, the lignite mine. The Spreewald again. The southern part, Welzow, that's the other lignite mine. And if we zoom in, you see different aspects of the geomorphology. It's not so important here. Okay, some facts about the lignite mining. Germany, also we are talking about a reduction of CO2, is #1 in lignite producing countries. Before China, before Russia, before Canada. So Germany is #1 lignite producing countries. We still produce 25% of our energy or power from lignite. There are three mining districts in Germany. That's the Rhineland, nearby Cologne, Bonn, Aachen. Then in nearby Leipzig in Middle Germany, and in East Germany in Lusatia we have another one. And Lusatia is the second largest district in Germany. There is a huge demand on land. So we just discussed this. The entire area affected by the mining is more than 2,000 square kilometers. And this area is defined by the groundwater lowering. So this is an open cast mining, and open cast mining means that if you want to get to the ore from the surface, you need to lower the groundwater, because the natural groundwater situation here is that the groundwater would be 2, 3, or 4, 5 meters above, about that, below the surface. But the lignite seam is sometimes 80 meters below surface. So you have to pump out all the water, and by pumping out the water, you produce these huge lowering of the groundwater. So more than 2,000 square kilometers of groundwater lowering and 850 square kilometers of active of land demand by the mining itself. You see these, here's Berlin again, Spreewald, then Cottbus, Jenschwalde, Cottbus Nord, and the southern parts. All these areas are former mines, and you may know that the GDR relied on almost 100% on lignite for producing power. So before the German reunification, there were more than 25 of these mines. And now we have 5. Actually, we have 4 because Cottbus Nord was closed some weeks ago. Now, the technique we are using here in Lusatia is a so-called strip mining technique. This is very special in that sense that we use a so-called conveyor bridge. And the conveyor bridge, which is used here in Jenschwalde, is called F60. F60 is for the capacity to transport 60 meters of overburden from one side to the other side with one process. That's what the conveyor bridge does not excavate the lignite. The conveyor bridge simply transports the material from the forefield to the reclamation site. And it has a maximum capacity of 60 meters. So the lignite seam in Jenschwalde is in a depth of about 80 meters, something like that. So smaller excavators have to dig out the material in the forefield until, or if to a point where there's 60 meters left, and then the conveyor bridge transports the overburden from this side to the heap side. And then by that process, the lignite is opened and the excavators transport this to the power plant, which is nearby. And this is an important point also from the economic view. 50% of the lignite is water. So economically, it does not make sense to transport the lignite far distances. So the power plant always have to be close to the mine. And it's a quite simple technique, but it's a huge technique. Yeah? So this machine has the height of the Eiffel Tower in Paris. Mm-hmm. Yeah, and we work in this area, and the other guys who deal with reclamation work in that area. This is one of the 2 slides which are in German, but I explain this. Yeah? So it's just a very recent publication we made for a conference, therefore I show it. So you see the strategy in sense of the soils here. No? You have the active lignite mine, the conveyor bridge. You have the spreader, which dumps material which is transported from the forefield to the reclamation site. And then here in that area, on the post-mining site, new soils develop, very young soils. And in the forefield, you have older soils, which are destroyed. And that's the part we talk about here, the destruction of the landscape in the forefield. And my story is that there are not only soils like the brown ones, which developed in the last 20,000 years by natural soil pedogenic processes, but there are also relatively young soils as a result of early human impact. Yeah? And therefore, we see, or we can identify some kind of a cultural landscape in the forefield of this mine. This is an aerial view of the lignite mine in Jenschwalde. So Cottbus would be down here. So this is Cottbus Nord, the smaller mine. This is, which is closed now. This is the mine Jenschwalde. This is the strip which opened the lignite, and you see this is the reclamation area. In German we call it recultivation, because we have a cultivation before, since in the land use of farming, and we want to establish a cultivation afterwards, a farming or a forestry. If you go to North America, they call it reclamation or renaturation, because often you affect a landscape which was not, where there's no anthropogenic use before. So in the forefield, the area is prepared for the mining, so there's a forest here. In this example, the forest is cleared, and then all the area is mined and then dumped here on this side. And this is the area where we work, and this is the power plant, and this is Peitz with the ponds here. So the strategy of the mining is the strip would be here in the south. This is again here in Schwalde. So the mine operates in this case from south to north, and with a velocity of about 500 meters per year. And the width can be up to 5 kilometers. So every year, an area of 500 meters depth and 5 kilometers width is destroyed. And the bright colors you see here in the forefield are all archaeological excavations, which is an obligation by law in Germany that once you have some kind of autobahn or these huge excavations, also small or huge mining operations, or also smaller ones, you have to check, is there some kind of archaeological remain in the subsurface or in the area, and this has to be paid by, this case, Vattenfall. So if you buy an area in Germany and you are unlucky, so to say, and you find some archaeological remain, you have to pay for the rescue of this remain, or at least for the surveying and the recording of the findings. So, and this is done by the State Archaeological Survey. The State Archaeological Survey operates with 15 to 20 people every day in the forefield, technicians, all kind of professions, and document all the findings here, because after 6 months the whole area is gone forever. So it's destroyed. What they do is they simply document it. Yeah? And this is what is interesting for us with the profession we have, and I will tell you some examples of the findings of the last years, just to show you the idea of this research and the studies. Quite interesting approach was the excavation of an Eemian lake basin. So the Eemian is the last interglacial 110,000 years before, something like that, where we had similar climatic conditions like today. And in a lake basin, you sometimes find remains of, if you're lucky, of humans, but at least of plants, here shovel of an elk or a moose, and I guess we will see some more spectacular pictures from my colleague later on. To make it short, here the special aspect of this research was that it was done directly in the mine, not in the forefield, but in the mine, which is quite unique. So normally they don't do that, because this is really the area where you have the heavy machinery in operation, and it can be very dangerous. So it needs some planning to do that. Yeah, but there was not a human finding, so the big finding is still in Messel. Okay, another aspect is show by this picture, and here you ideally see this concept of what we call the geopedology, because what you see is the topography or the geomorphology, so the landform. So this landform is a dune, so it was formed by wind-blown processes, or by wind-blown, or by aeolian dynamics, as we call it. So this is aeolian sand, and it forms this dune. So we have the substrate, or the subsurface, and we have the landform. But the interesting part here is the black, the white, and the red colors, which is a soil. So the soil is embedded in this landform and in this substrate that builds up the landform. And by analytics, as I described, by dating techniques, we can identify, okay, how old is this soil here, how old is the aeolian cover of the area, etc. And this is the approach where we say, okay, we can reconstruct the landscape development. In this case, we can reconstruct, okay, this part, the lower part here, is characterized by just natural dynamics, and this is the natural soil, which we call the Holocene soil, the soil development of the last 10,000 years, and then later on, either by human activity or by natural processes, there's an aeolian deposition of younger material, and on top there's a very shallow soil, so a young soil, as I showed you before. Another example, a very nice one, giving us evidence of, direct evidence of the early farming. So in the field, you sometimes see these kind of structures which are not really good to photograph or to make picture of it. So this is a so-called ridge and furrow system. Ridge and furrow systems, you see a picture here, much better, with this linear structure. So this is a forest, this is farmland, a recent farmland, so this is covered by trees. And under the forest canopy, you see these linear structures, and these linear structures are these ridge and furrows, which are produced by a special plowing technique. And the plowing technique was in that manner that the farmer used this plow just in this direction, and then he turned and moved that direction, and then he turned again, and something like that. So with this technique, he built up a little elevation here and a ditch on this side. And so the structure basically mirrors the former size of the farmland the farmer used. So these ridge and furrow systems are often found in our area. Another evidence for early agriculture are these structures in the sand caused by this hook plow, and this hook plow could be dated with Dendro age to about 1,000 years before. This is the Slavic period here in the area. So this is an archaeological excavation. By the archaeological finding of these plowing structures and the dating, we know that 1,000 years before there was a farming in the area using the soils and producing this structure. And with farming, in an area where we have very dry conditions, where you have a lot of sand, where there is high wind speed, we have the effect of soil erosion, of wind erosion, as we can see nowadays. For example, this picture was taken some years ago, and it's not a gravel road, it's a paved road, yeah? But it's completely covered with sand. So also the ditches here are completely covered with sand, meaning that from the adjacent farming land, the sand was blown over the area, like you see here, over the landscape, and just destroyed the vegetation, the smaller ones, and produced these aeolian sediments, as we have seen in other outcrops, as in a section of the last 1,000 years. One finding I will explain a little bit more in detail is also in Jenswalde. So you see this is the year, March 2008, April 2010, June 2011, and then so these areas already gone, and we had a soil profile here in that area, in this glacial outwash, or in this Urstromtal, this ice marginal valley. And we see in the section the plowing marks, so we know there was agriculture. And this is the profile with the horizon here, this dark one. So this is the former plowing horizon. This is a top view. This is the section in the profile. And on top of this plowing horizon, we have this brighter material, which is an aeolian sediment. So by dating this plowing horizon to these ages, about 1,000 years before, we know that there was plowing in the area 1,000 years before, and then afterwards an aeolian sedimentation with sand. So we can reconstruct the landscape that we know that there was some farming, but then the farming was dismissed, so gone, and later on we have destruction of our farming land by aeolian sedimentation. I don't know how much time I have. Okay, last part is the focus on charcoal production. Charcoal was the energy source till the end, the mid of the 19th century, something like that, before the use of hard coal. So for any mining and for any production of ores or melting, you needed charcoal. So charcoal was produced by the forests, and you see some pictures from archives, but also in the 60s from different areas. These are one from Lusatia here. So they took the wood and produced in these charcoal kilns the charcoal for the iron works to smelt the iron and produce guns. Often guns, like the Swedish produced a lot of guns, and to have weapons for the war. And in our area in Jenswalde, we find a lot of these remains here. You see these circles. There's one, there's another one, and these circles are remains of the charcoal kilns, because what they did, they produced these piles of wood, then they made the charcoal, took 10, 14 days, and then they just harvested the charcoal. And then it was transported to the nearby ironwork, where it was used in the ovens to smelt the iron. And in the landscape remained these circles, because this is a ditch which was produced in the, surrounding the ironwork. So these were circular charcoal kilns. So if you are lucky, you find remains of the charcoal here. The archaeologists did a lot of surveying and classified these charcoal kilns according to the ground plans. So we have ones, very simple ones, then some containing posts, others with pits outside, then multiple ones I showed you, or even ones with plowing marks. So what we do now since several years, we want to get a a better idea of what this means for the landscape development, and the interaction of humans with the natural and the cultural landscape. And so this is a long-term project we established some years ago. So we have several aims you see here, but I just explain the first parts to study the spatial dimension of the charcoal production and how to assess this with LS data and produce a database of charcoal. This is a historic map from 1850 or 1845. The first survey, which was done in Prussia. Cottbus would be down here. So this is Peitz. You have already seen in one of the area views with the ponds. At Peitz, there was the Ironwork where they produced the these guns, etc. And so from the surrounding, they needed the charcoal. And this is the Jenschwalde area, so these villages are already gone, so the mine is now about here. And so the black line is the former area of the forest, which is locally called a Heide, so that's some kind of a forest. And all the red dots are excavated charcoal kilns. Up to now, there's more than 1,000 charcoal kiln remains that have been excavated and surveyed. So this is by far the largest archaeological known charcoal kiln field in Europe. An interesting feature of these charcoal kiln remains is that due to the construction, so this was the shape of the charcoal kiln once it was built. So then they took out the charcoal, and what remained is a little mound here and a little ditch surrounding this charcoal kiln remain. So from a top view, you find these ditches here as circular structures and a little mound in the center. Taking now these high-resolution ALS data, so these are airborne laser scanning, or these are then produced so-called shaded relief maps, SRM. So with this high-resolution data, you can analyze this structure. So you see this circular structure here, yeah? And if you make cross-sections through this structure, the elevation here is meter above sea level, that's 84.2 to 85. So this whole scale is just 80 centimeters, 0.8 meters. And you see very small differences. So this is the ditch, and there's a ditch, and there's a little mound, and there's a ditch, and there's a little mound in the middle. So as a result, in these SRM images, you find all over these circular structures, yeah? Here and here, here and here and here, which can be identified as former charcoal kilns. So what we then call charcoal kiln remains. Coming back to the Jenschwalde site, one of the PhD students compiled all the data for this former forest site. And you see the black one here now are the excavated one, and the red one are the one which are identified by these laser scanning analysis. And in a first approach, we identified just for the Jenschwalde site 5,000 potential charcoal kiln remain ground plans just for that one site. Later on, we have seen that we have to revise this, and we now are for sure that for this site we have 1,500 charcoal kiln planes. Once we have the data, we can do some statistic on it. We can prove, we can show, or we can analyze how large, what is the diameter, do we have small ones, do we have large ones, something like that. And we can analyze the spatial distribution of the different sizes, so we can classify these, the smaller ones, the medium ones, and the very large ones, and we can show where are these ones located, especially in relation to the former ironwork. Okay, of course we want to know what ages do you have. Age can be determined by tree ring analysis or dendro analysis. The first published data set was from this year with 13 ages or 16 ages, and we have now new dates up to more than 60 ones are dated, and we have ages between mid of the 16th century to mid of the 19th century, and that's exactly the range when the ironwork piles operated. So, concluding that, as I mentioned, we have detected 5,000 potential charcoal kiln sites in an area of 30 square kilometers. By reassessment or re-evaluation, we can confirm at least 1,500, and this number for the one site we can conclude that we have lots of these sites here in the North German lowland, but it's simply not have been studied before. And we have several more questions to answer, of course. What is the effect on the forest, so how much wood was used for the production of the charcoal kiln, and then we want to expand or extend this research to other regions and using automatic detection procedures for that. So with the project started here directly in the mining area, we now go to other areas which are not mined in this site, and first result of this ongoing project shows us, yes, we have lots of these charcoal kilns here, and really thousands and thousands of these charcoal kiln remains still hidden under our forest canopy. This is just it's very complicated. Just refer to the literature. This is Anna Schneider, a postdoc with my group. She established an automatic mapping routine to identify all these charcoal kiln remains with GIS, because the first approach we made in Jenswalde, this was just done manually by a person sitting on a computer, and this was also the reason as we had this high failure percentage. So because it's just a matter of the operator of the machine that you produce a lot of failures. And she started now to work in other areas north of Jenswalde, and so to go back here. So Peitz is here, Jenswalde is here, and the next slide shows the area north of it. And again, this is the topography. This is are the charcoal kiln sites, and this is the density calculated for this. So again, we see thousands of these charcoal kiln remains here in the area. Okay, at the end, I would like to emphasize that this finding is not a regional one. So it's a very recent one. So it's really fascinating to see that we have now proof of these charcoal kiln remains, but there are other areas over the world where we find these charcoal kiln remains. And I just returned from the US in October, where I did some field work together with a colleague from the University of Connecticut. This is a map of Western Connecticut, so New York City would be down 150 kilometers to the southwest. And all these blue points, or these clouds of blue points or dots, are charcoal kiln remains. And the yellow dots here are the ones we studied. And if you look, this is again SRM image. You see all the dots here, yeah, all over the area. So the whole, and it's completely forested nowadays. So the whole area is full of these charcoal kiln remains. We did some trenching on it, and you see in this example how, so this is the charcoal kiln platform, and this is how the charcoal kiln platform looks in the soil profile. You see these dark structures here, the dark colors, so these are the remains of the charcoal kiln production. And interestingly, so these are two pictures from the same, so the one is from here, the one is from that point. You see that this picture, you just have one dark layer, and here you have one dark layer, a second dark layer, and a bright layer. So this is a proof for us that there was at least 2 times the site was used for charcoal production. 2 pictures at the end. So this is from a book called Connecticut Mining. So we were exactly at this site. So this is from 1905. You see the area is completely cleared for the charcoal production. And if you go nowadays to this area, it's completely forested again. So once you stand here, you would not realize that 150 years ago it was completely deforested. Okay, that's it.